Welcome to our continuing discussion on unidirectional flows, unsteady flows, where we were looking at different solution methods for flows that depend upon position and time. Variation in position is only along one direction, what I have called so far the z direction, okay. And there could be a variation in time as well. We looked at two solution procedures, one for transport into an infinite fluid, where we looked at the similarity solution procedure, where we could reduce from two independent variables, time and z, to just one similarity solution based upon dimensional analysis alone, and that reduced the equation from a partial differential equation to an ordinary differential equation, and that we were able to solve in order to find the profile of the concentration, temperature or momentum. When the diffusion is in a finite channel, the thickness of the layer of fluid also is important, and one could use scaling on the basis of that thickness as well. In that case, I showed you how to use separation of variables, where we write the conservation the dependent field, temperature, concentration or momentum, as the product of two functions, one only a function of space, the other only a function of time, separate out the two and get individual equations for each of these two components. Each of these can now be solved in order to get a solution for the entire concentration, temperature or velocity fields. And this solution procedure, we had to have homogeneous boundary conditions in one coordinate, in this case the spatial coordinate. The temperature, concentration and velocity were both 0 on both bounding surfaces, but there was an initial forcing at initial time, and I showed you how to get all the constants in those equations. So, that was the separation of variables technique. And last lecture we discussed how to analyze oscillatory flows. In this particular case, we had a channel in which the top plate was stationary, the bottom plate was oscillating with a well defined frequency. And there is an imposed time period in this case, in contrast to the previous problems where we just imposed an initial condition and then let the system evolve in time all the way to t going to infinity. So, in this particular case we do have an imposed frequency. Okay. The momentum conservation equation was identical to what we had for all other cases. There is no source or sink. Okay. So, we had this momentum conservation equation, where nu was the kinematic viscosity. The boundary conditions were that velocity is 0 at the top plate, velocity is sinusoidal at the bottom plate with a very well defined frequency. Okay. We had defined scaled variables, z star is equal to z by h. H is the natural length scale because it is the width of the channel, and ux star is equal to ux by capital U, where u is the velocity with which the bottom plate is being oscillated. We also have an intrinsic time scale in the problem. So, we can define a non-dimensional time as t star is equal to omega times t. And when we put all of these into the differential equation, we ended up with a dimensionless number R e omega, which was defined as omega h square by nu, where h is the thickness and nu is the kinematic viscosity. Okay. And the boundary conditions are at z star is equal to 1, ux is equal to 0, and at 0 ux is just equal to cos t. So, this cos function varies between -1 and +1, okay, and it is sinusoidal in time. And we looked at a simple way to solve it. This cos function at the boundary is inconvenient in general to deal with. So, we defined a complex velocity field such that the actual velocity which we would like to obtain is the real part of this complex velocity field. In terms of the complex velocity field, the equation, the governing equation is exactly the same, because the Reynolds number is a dimensionless number, it is real. At the boundaries we have the complex velocity is 0 at z is equal to 1, because there is no motion there. At z is equal to 0, the complex velocity is e power I t. The real part of e power I t is the same cos t with which you are forcing the real velocity field. Okay. So, therefore, if I take the real part of the equation, I get the equation for the real velocity field. If I take the real part of the boundary conditions, I get the boundary conditions for the actual velocity field. So, if I can solve the equation for this complex velocity field and take its real part, I will get the actual velocity field. Okay. That was the first simplification. The second one was that the equation is linear in u x plus. Okay. So, the equation that I have is a linear function of u x plus, and it is being driven by a sinusoidal velocity profile at the boundaries. U x plus is equal to e power I t. So, the equation is linear, the driving is sinusoidal, the response also has to be sinusoidal with exactly the same frequency. Okay. So, that was the second simplification that I used. That straight away permitted me to write u x plus as e power I t star times something that is only a function of z. Okay. So, that was a significant simplification. U x plus I separated out into two parts, one which is dependent on time, okay, and the other which is dependent only on space. Implication of that is that at every point within the flow, the velocity is oscillatory with exactly the same frequency as the frequency of the bottom surface. Okay. It can have a phase that is different from the phase of the bottom surface, but it is oscillatory at exactly the same frequency. There can be a phase shift. The phase shift can be different at different locations, but the frequency is exactly the same. Okay. And since I know the dependence on time exactly, I can do the time derivative, and I finally get an equation which is an equation dependent only upon the z coordinate. It is a second order differential equation, can be solved quite easily as we saw in the last class. Okay. The boundary conditions, since the boundary condition for the complex velocity is e power I t at the bottom surface, for this u x tilde, the boundary condition has to be u x tilde is equal to 1, because this times e power I omega t is the complex velocity field. Okay. So, now both the differential equation and the boundary condition are independent of time when expressed in terms of this variable u x tilde. Okay. They depend only upon space. So, once again I have reduced the equation from a partial differential equation in time and z to just an ordinary differential equation in z alone, knowing that the variation in time is going to be sinusoidal with the given frequency at all instants of time at all locations. So, we solved this quite easily and subject to the boundary conditions to get a solution. Okay. And we took the real part of that solution to find out what is the actual velocity field. This of course has to be solved numerically, okay, as a function of time. Okay. However, you can get some additional physical insight into this by just looking at the limits. One is the limit where r e omega is small compared to 1, and the other is the limit where r e omega is large compared to 1, because that is the only parameter in the problem. Okay. And we looked at the physical meaning of r e omega small compared to 1. In that case, you just get the solution as the steady solution, 1 minus z times cos t. Okay. If the steady velocity were u x is equal to 1 on the bottom surface, the steady solution would have been 1 minus z. However, the solution is varying in time, and so I am just getting 1 minus z times cos t. Okay. So, basically the solution in the limit r e omega small compared to 1 is the same as the steady solution, except that the velocity, okay, the bottom surface is the instantaneous velocity, a function of time at that particular instant, whatever the velocity is, that is the maximum velocity at the bottom, and you get a linear velocity profile. And we looked at physically why that is so. One can interpret the Reynolds number r e omega, omega h square by nu, as the ratio of h square by nu divided by 1 over omega. H square by nu has dimensions of time. It is the time it takes approximately for momentum to diffuse over a length h. So, it is the time it takes for a momentum disturbance generated at the bottom to diffuse all the way to the top of the channel. 1 over omega is the time period of the oscillation. So, when the Reynolds number is small compared to 1, the time required for momentum diffusion is small compared to the period of the oscillation. So, whatever the velocity at the bottom plate, the momentum diffuses instantaneously, because the velocity is varying much slower than the time than the rate of diffusion of momentum. And because of that, at every point in the oscillatory cycle, the momentum field equilibrates to the steady value it would have had for that particular bottom velocity. Okay. So, in the case of r e omega small compared to 1, we recover the linear velocity profile, except that the velocity at the bottom surface of that linear velocity profile is the instantaneous velocity of the bottom plate. That is restricted to the case where the time required for momentum diffusion is small compared to the time required for the period of oscillation. The opposite case, when r e omega is large compared to 1, we saw that there is an exponential decay in the velocity field into the fluid. That decay takes place over a length scale which is approximately square root of nu by omega. Okay. Nu is the kinematic viscosity, has dimensions of length square per time, omega is the frequency. So, square root of nu by omega is the time it takes, okay. The square root of nu by omega is the distance to which the momentum diffuses within a time period of 2 pi by omega, or within the time required for the oscillation. So, this is the distance over which the diffusion takes place over the time period 2 pi by omega, and the Reynolds number can also be interpreted as h by nu by omega power half the whole square, which is the square of the ratio of h and the distance to which momentum diffuses. So, if Reynolds number is large, that means h is large compared to the distance over which the momentum diffuses. It looks like momentum diffusion into an infinite fluid. Okay. And because the distance h is large, the momentum diffuses only to a finite distance before the plate stops its forward motion and comes backward. Okay. So, over a time period comparable to 2 pi by omega, the distance that the momentum diffuses is given by square root of nu by omega, and that is the distance, the penetration depth or the boundary layer thickness over which this velocity is finite. Okay. And we got a solution also for that, okay, for that velocity field in the limit of r e omega large compared to 1, and this solution is not in phase. Okay. It has both sine and cosine functions, okay, in time. So, this solution is not exactly in phase with the driving frequency, even though the frequency of oscillation of the velocity at every point is exactly the same. Okay. So, one last comment about the discussion on oscillatory flows. So far, we have solved only for u x at the bottom being oscillatory in time. Okay. What we actually solved for was a cos function. So, okay. What we actually solved for was a cos function. Okay, sine function will be exactly displaced by pi by 2. Okay, but what we solved for was a cos function. One could have a forcing which is not exactly a sine function, okay, or a cos function. Okay. For example, one could have a forcing that looks something like that. Okay. But so long as it is periodic in time with a frequency omega, okay, so long as it is periodic in time with a frequency omega, this thing can always be written as the sum of cos and sine functions, which are the lowest harmonic and its submultiples. that is the period is the frequency is equal of this is omega, this is 2 times omega, 3 times omega, and so on. Okay. So any function can be written as can be decomposed into its fundamental mode, the frequency of the largest oscillation omega plus all of its harmonics. Okay. And so I can solve individually for each of these. Okay. I can solve individually for this function, and all other harmonics. Okay. Solve the equation, get the solution here for each of these harmonics, get this solution for each of these harmonics, and then add them all up, and I will get the solution for this more complicated form of the wave. Okay. That is because in Fourier transforms we know that any function that is periodic with a frequency omega can also be can always be decomposed into a fundamental mode plus all of its higher harmonics. It is an infinite series, but still the decomposition is always possible, and because the decomposition is possible, this procedure for an oscillatory flow can be applied to any waveform, not just a sinusoidal waveform, but to any waveform. Okay. Okay, so in that sense it is more general. All I require is that there should be bottom plate velocity should be periodic in time with the frequency omega. Once that condition is satisfied, does not matter what the waveform is, I can always apply this solution procedure. Okay. Okay. So that completes our discussion on oscillatory flows. We will come back and see later on oscillatory pressure driven flows. Okay. But before we go there, I would like to first spend some time on what happens when there are sources or sinks within the field. Okay. So far we always took two plates, one had one temperature, the other had another temperature, and there was no generation or destruction of mass momentum energy within the domain. Okay. What about sources where there are, what about cases where there are sources or maybe there are forces acting on the fluid within the domain? In that case, how do we solve these problems? Okay. So, we will just look at a few brief examples of this. Okay. In the case of momentum transfer, the simplest case that you can think of is the flow of a fluid layer down an inclined plane. Okay. So, I have an inclined plane inclined at some angle theta to the horizontal, and the acceleration due to gravity is acting downwards. Okay. And I have a layer of fluid flowing down the plane. Okay. And we will get a velocity profile that looks something like this. Okay. So, as usual I take x as the flow direction and z as the direction in the perpendicular to the flow. Fluid velocity is in the x direction and the velocity is varying only in the z direction. There is no change in velocity as you go along the x coordinate. Okay. So, if I were to write a momentum balance equation for this, right, I would have to write it of the form dux by dt is equal to nu times d square ux by dz square. Okay. However, there is also a force acting on this due to the gravitational field. Okay. There is a force acting on this along the x direction due to the gravitational field because it is inclined at a fixed angle to the horizontal. Okay. Once again, I will take the layer thickness as h, and I would like to find out what is the velocity profile as a function of h. Okay. What are the boundary conditions for this case? At the bottom surface there is a solid wall which is not moving, therefore, I require that at z is equal to 0, ux is equal to 0. What about the top surface? Okay. At the top surface, the fluid layer is in contact with a gas or with vacuum. Okay. Even if it is in contact with a gas, the viscosity of the gas is much smaller than the viscosity of the liquid. Okay. Liquids usually have viscosities of 2 to 3 orders of magnitude higher than gases. Therefore, the viscosity of the gas is much smaller than the viscosity of the liquid. The shear stress applied by the gas is negligible compared to any stress that would be exerted by the liquid. Okay. Therefore, at the free surface itself, since the viscosity of the gas is small, the shear stress exerted by the gas is small. At the interface, you require continuity of stress between the liquid and the gas. That means that at z is equal to h, you require that the shear stress in the liquid go to 0, okay, because the viscosity of the gas is small compared to the viscosity of the liquid. That means that the shear stress that is exerted in the gas is small compared to the internal stresses within the liquid. So, as you approach the interface from the bottom, you require that the internal stresses in the liquid should go to 0, so that they match with the stress in the gas. Okay. Tau xi is equal to 0 implies that mu times dux by dz is equal to 0, or the boundary condition is dux by dz is equal to 0. Okay. So, the derivative of the velocity with respect to z has to be 0 at the top surface. Okay. I should put in f(x) by rho, force per unit volume. Okay. So, what is the force acting in the horizontal direction? Okay. This is, as I said, a force per unit volume. Fx is a force per unit volume acting along the x direction. The component of the gravitational acceleration is g times sine theta, okay, along the x direction. Okay. The component of the gravitational acceleration along the x direction is equal to g times sine theta, because theta is the angle of the inclined plane with respect to the horizontal. Therefore, the force per unit volume acting on every volume of fluid has to be g times sine theta times the density. So, this is the force acting along the x direction on every differential volume of the fluid. Okay. So, therefore, if I put this into the governing equation, I get dux by dt is equal to nu times d square ux by dz square plus g sine theta. Okay, so, that is my equation for the velocity field. How do I non-dimensionalize my variables? Once again, h is the natural length scale in the z direction. So, I can define z star is equal to z by h. Okay. What about ux? Okay. In the previous examples, there was a well defined velocity of the boundary. I had the boundary condition ux is equal to capital U at z is equal to 0 and ux is equal to 0 at z is equal to 1. In this case, the boundary conditions are both homogeneous. Okay. There is no velocity at the boundary. Okay. Ux is equal to 0 on one surface and the derivative is 0 on the other surface. So, there is no velocity scale emerging from the boundaries. Okay. However, there is a velocity scale that emerges from the fact that there is a body force acting on the fluid. Okay. So, therefore, what I can do is to divide throughout by g sine theta and use that to scale the velocity. Okay. So, if I divide throughout by g sine theta, I will get 1 by g sine theta partial ux by partial t is equal to nu by h square g sine theta partial square ux by partial z star square plus 1. Okay. Now, this thing gives us a clue about how we should scale the velocity. because if I define ux star is equal to ux times nu by h square g sin theta. If I define it this way, then that entire term becomes dimensionless. 1 is dimensionless anyway. Okay. So, this gives us a way to scale the velocity. Okay. And you can easily see that it is dimensionally consistent. On the top we have a velocity which is length per unit time. Kinematic viscosity is length square per unit time. Okay, so, you get length cubed by time square. On the bottom h square length square and g is length per unit time square. So, length cubed by time square. So, it is dimensionally consistent. Okay. So, therefore, in this case the velocity scale is coming from the forcing within the fluid, not from the boundaries. Okay. So, if I put this in, then I will get an equation of the form partial ux star by partial t star is equal to partial square ux star by partial z star square plus 1, where z star is equal to z by h and ux star is equal to ux nu by h square g sin theta. Okay. And you will find that t star is the same that I had earlier. T star will be equal to t nu by h square. Okay. So, the time scale is once again scaled by the time it takes for momentum to diffuse across the entire channel. The distance is scaled by h itself, and ux star has a scaling which is given by a balance between the body forces. Okay. So, the scaling for ux star that we got was by taking a balance between the body forces which are here and the viscous stresses over a layer of thickness h. Okay. So, this has given us the scaling for ux star. Okay. So, what are the boundary conditions? ux star is equal to 0 at z star is equal to 0 and dux at dz is equal to 0 at z star is equal to 1. Okay. So, these are the boundary conditions for the flow. Okay. And let us solve this differential equation subject to boundary conditions. Note that the boundary conditions are homogeneous. Okay. The boundary conditions do not contain any inhomogeneous term in them. So far, whenever we have solved diffusion in a channel, the boundary conditions have contained an inhomogeneous term. There was a velocity u at the boundary, there was a temperature T star is equal to 1 at the boundary, or concentration C star is equal to 1 at the boundary. In this case, the boundary conditions do not contain any inhomogeneous terms. The driving of it comes from the source within the equation itself. Okay, the driving comes from the existence of a source within the equation itself. Okay. So, first thing, steady solution in the absence of any time dependence. Okay. The equation becomes d square ux by dz square plus 1 is equal to 0. Okay. And the solution is quite easy to get. The solution for this is ux is equal to z minus z square by 2. Okay. It is easy to verify that this solution z minus z square by 2 satisfies both of these boundary conditions. At z is equal to 0, ux is equal to 0, and at z is equal to 1, the derivative is equal to 0. Okay. So, this satisfies both boundary conditions. So, this is the final solution for the velocity profile, at steady state. I express this back in terms of the dimensional velocity. Okay. Ux is equal to ux star into h square g sin theta by nu. Okay. And this will be equal to g sin theta by nu into z h minus z square by 2. So, this is a parabolic velocity profile. Okay. So, the velocity profile for the flow down an inclined plane is quadratic in the velocity z. It starts off at 0 and then you get a parabolic velocity profile, and at z is equal to h, the derivative of the velocity with respect to z is equal to 0, the shear stress is 0, and therefore, it satisfies the stress balance condition between the fluid and the gas that it is in contact with. Okay. So, this is the velocity profile for the flow down an inclined plane. Okay. Now, this is the steady solution. Now, what about the unsteady solution? Okay. So, we can consider, for example, the flow down an inclined plane. Okay. This is the final steady solution, and the solution satisfies the boundary conditions at z is equal to 0 and z is equal to h. Okay. So, the equation is d square dux by dt is equal to d square ux by dz square plus 1, okay, in non-dimensional terms. The boundary conditions are ux is equal to 0 at z equal to 0, and the stress is 0 at z is equal to 1. Okay. Now, we want to solve for the unsteady case. Okay. So, the idea is as follows. Initially, the film is horizontal, so that the velocity is identically equal to 0. At time t is equal to 0, you tilt the film to this angle. Okay. You tilt it to an angle theta, and the fluid starts to flow. The flow is still fully developed in the sense that there is no variation in the x direction. Okay. However, the flow does increase with time, okay, to reach the final steady state. Okay. So, because of that, you require to find out what is the profile at intermediate times as it is evolving to the final steady state. Okay. Similar to the problem that we had solved for the instantaneous startup of a plate at using separation of variables. Okay. So, this is also an initial condition which is that at t is equal to 0, ux star is equal to 0 for all z star. Okay. At time t is equal to 0, the velocity is 0 everywhere. Okay. So, we have to solve this equation, okay, subject to the initial and boundary conditions. The solution procedure is similar to the separation of variables solution procedure that we had earlier. Okay. So, we have to follow the same steps in order to get the solution for this as well. There is a complication when you have body forces, and it is in order to point that out that I am going through this solution procedure. Okay. So, as in the previous case, okay, I will separate ux into a steady part plus a transient part. So, I separate the velocity profile into a steady part plus a transient part. The steady part, I already know what the solution is. Okay. The steady part satisfies the differential equation d square ux by dz square plus 1 is equal to 0. The steady part satisfies this equation, and we got the steady solution is equal to z minus z square by 2. Okay, so we already got the steady solution. Okay. Now, the total differential equation satisfies this equation, okay, satisfies this equation, and the steady part satisfies this equation. Okay. Subtracting the two, I can find out what is the equation for the transient part. Okay. So, from the equation for the total velocity profile, I subtract out the equation for the steady velocity profile, and note that dux s by dt is equal to 0 because it is steady, it does not depend upon time. Okay. And then I will get an equation for the transient part alone, okay. Dux t by dt is equal to d square ux t by dz square. So, that is the equation for the transient part alone. Note that the equation for the transient part does not contain an inhomogeneous term similar to this one. Okay. The equation of the transient part does not contain this inhomogeneous term. Okay. Once I have the equation, I also should impose the boundary conditions. Okay. For the total velocity field, I have ux is equal to 0 at z is equal to 0, derivative is 0 at z is equal to 1. For the steady part, I have exactly the same boundary conditions. Ux is equal to 0 at z is equal to 0, and ux is, and the derivative is 0 at z is equal to 1. That means that the equation for the transient part will also have boundary conditions and dux by dz. Okay. So, it has the same boundary conditions as the steady part and the total velocity profile. Okay. However, the initial condition is different. Initial condition for the total velocity field is ux is equal to 0 for all z at t is equal to 0. The steady part, of course, is independent of time, it is the same at all times. Okay. Therefore, the initial condition for the transient part has to be ux transient is equal to minus ux steady at t equal to 0. Okay. Only if ux transient is equal to minus ux steady, the sum of the two will be equal to 0, which means that the total velocity ux will be equal to 0. Okay. So, one has to be careful while defining the initial and the boundary conditions. Okay. In the equation itself, when I subtract out the equation for the steady part from the total equation, since both of them contain the inhomogeneous term, the equation for the transient part does not contain any inhomogeneous term. Okay. So, this equation for the transient part does not contain any inhomogeneous term. The boundary conditions were homogeneous for both cases, but we have to be careful about the boundary condition for the transient, I am sorry, we have to be careful about the initial condition for the transient part, okay, because it will contain, okay, a contribution due to the initial condition for at time t is equal to 0. Okay. So, to summarize, the equation for the transient part is dux transient by dt is equal to d square ux transient by dz square. Okay. The boundary conditions are ux transient is equal to 0 at z is equal to 0, and ux transient the derivative 0 at z star is equal to 1. And the initial condition was ux transient is equal to minus ux steady is equal to minus of z minus z square by 2, okay, at t equal to 0. Okay, so we have to solve this equation with these initial and boundary conditions. The method is exactly the same, separation of variables. Okay. Note that now I have an equation which is entirely homogeneous. Okay. That is essential for the separation of variables procedure, okay, as I will show you. Okay. If I substitute ux transient is equal to theta of t times z of z star into the differential equation, then I get partial theta is equal to theta times d square z by dz star square. Okay. And if I divide throughout by theta times z, I get 1 by theta partial theta by partial t is equal to 1 by z partial square z by partial z star square. Once I have this, the left hand side is only a function of time, the right hand side is only a function of z, and I can effect a I can set both of those equal to constants. If on the other hand I had an inhomogeneous term here which was looked something like plus 1 in the present case, in this case I would have got something that goes as 1 over theta times z, okay. And then I could not have done a separation of variables because the right hand side also contains a function of time. So, it is essential when we do separation of variables that the equation be homogeneous. It should not contain any inhomogeneous terms, and you reduce it to a homogeneous equation by subtracting out the steady part which already has the inhomogeneous term in it. Okay. Because we do not have these terms, we are able to do a separation of variables solution. Okay. So, it is essential. If you recall, when we did the flow between two flat plates, we had inhomogeneous boundary conditions. U z was equal to 0 at z equal to 1, I am sorry, t was equal to 0 at z is equal to 1, 1 at z is equal to 0. Okay. However, when we subtracted out the steady part, for the transient part alone we had temperatures equal to 0 on both surfaces. Okay. And a similar reduction and because of that we got homogeneous boundary conditions on both surfaces. A similar reduction has to be done when there are inhomogeneous terms in the equation as well due to sources, sinks, body forces and so on. Okay. Once that is done, then I can set both of these equal to constants. Okay. What constants should they be? Once again 1 by z d square z by dz star square. If it were a positive constant, I would get exponentially increasing and decreasing functions, and it would not satisfy boundary conditions. If it were negative constant, I would get sinusoidal solutions, okay. And then there is a chance to satisfy boundary conditions if I choose the constant appropriately. So, this I can write it as a negative constant beta n square. Okay. That means that z was equal to a sine beta n z star plus b cos of beta n z star. And then I have the boundary conditions on the velocity at z is equal to 0, capital Z is equal to 0, which means that b is equal to 0. Okay. At z is equal to 1, I have at z is equal to 1, I have the boundary condition dux by dt is equal to 0. I am sorry, I have dux transient by dz is equal to 0. Since all of the dependence on z is contained within the function capital Z itself, okay, if I want to satisfy the boundary condition, okay, I need to ensure that dz by dz star is equal to 0, okay, at z is equal to 1, okay, because the derivative of velocity with respect to the z coordinate has to go to 0. Velocity is the product of two functions. One is a function of time, the other is a function of z. When I take the derivative of velocity with respect to z, this first theta is independent of z, and therefore, I just get dz by dz star. And if dux by dz star has to be 0, that means d of capital Z with respect to dz star has to be equal to 0. Okay. And this implies that beta n has to be the slope of the sine function is equal to 0, sine beta n z star, d by dz star of that is equal to 0. That means that cos beta n z star has to be equal to 0. That means that beta n has to be equal to half 3 by 2, 5 by 2, etc. to infinity. Okay. Only if beta n is these values will you have the slope of the sine function being 0 at z is equal to 1. Okay. I can write this compactly as n plus 1 to n plus 1 by 2. Okay. So, for n is equal to 0, it is half, for n is equal to 1, it is 3 by 2, n is equal to 2, it is 5 by 2, and so on. Okay. Therefore, my solution for the function z is a sine of 2n plus 1 by z by 2. Okay. I made a mistake in the previous one. This should be pi by 2 Okay. So, that is the equation for capital Z. Okay. And I also have 1 by theta d theta by dt is equal to minus beta n square is equal to minus of 2n plus 1 pi by 2 whole square. Solving this, I will get the exponential function theta is equal to e power minus 2n plus 1 pi by 2 the whole square times t. Okay. So, that is the final solution. Ux transient will be equal to theta times z, which is equal to a times sine whole square t star. So, this is the solution. This satisfies the equation for any value of z. So, the most general solution is a summation n is equal to 0 to infinity of a n times this, a linear combination of all of those solutions. How do we determine the coefficients a n? Using the orthogonality relations once again. Okay. So, for this particular problem, if you recall, for the flow in a channel, the basis functions were sine of n pi z by n pi times z star, whereas here the basis functions are 2n plus 1 pi z star by 2. Okay. So, I define S n is equal to sine of 2n plus 1 pi z star by 2. Okay. And the orthogonality function, the inner product Sn comma Sm, okay, is equal to integral 0 to 1 dz star Sn times Sm, which is once again equal to delta Mn by 2. Okay. You can work it out for this function as well. It gives you the same identical result as that for sine of n pi z. Okay. So, now I have to use the orthogonality conditions at the initial time t is equal to 0. Okay. At t star is equal to 0, right, ux t is equal to summation a n sine of 2n plus 1 pi z by 2, which is equal to summation of a n times S n. Okay. That is equal to minus of the steady solution, which was minus of z minus z square by 2. This is the minus of the steady solution. Okay. So, how do I find out the coefficients n? I take the inner product of both the left and the right hand sides with respect to Sm. Okay. So, summation of a n Sn comma Sm is equal to the inner product of z star minus z square by 2 comma Sm. Okay. This is equal to summation a n into delta m n by 2, which is minus integral d z of z star minus z star square by 2 sine of 2m plus 1 pi z by 2. Okay. So, this is a m by 2, and you can work out this integral quite easily to get a solution which is minus 1 by pi cubed into 2m plus 1 by 2 the whole cubed. Okay. And therefore, a m is equal to minus 2 by pi cubed into 2m plus 1 by 2 the whole cubed. Okay. So, that is the final solution. Okay. Ux transient is equal to minus summation n is equal to 0 to infinity minus 2 by pi cubed sine okay into the exponential part. So, this solution has all of the features of the previous solution by separation of variables. You have a series of harmonics, complete basis set, and the higher order terms in the series decay exponentially in time, and as n increases, the rate of decrease exponentially in time is faster. Okay. So, these have the same characteristics as the solution for the flow between flat plates, except that the basis functions are now slightly different. In the previous case, we required the basis functions to be 0 on both boundaries. So, it had sine n pi z. The present case, we require the basis functions to be 0 on one boundary and the slope to be 0 on the other boundary. That is the only difference. And because of that, the basis functions are sine of 2n plus 1 pi z by 2, okay, and they have an exponential decay. The decay rate will be approximately the same in both cases, because 2n plus 1 by 2 for large n is approximately equal to n. Okay. So, this gives you a flavor of how one solves the separation of variables for this particular case, when we did the separation of variables for the flow between flat plates, we had to ensure that the velocity on both surfaces for the transient part was 0. In this case, we had to ensure that there was no inhomogeneous term in the equation of motion. Okay. So, that is the only difference. Okay. So, this is a second example of separation of variables that I have showed you in order to solve the transient problem. Okay. So, this is an example of momentum transfer where there are sources and sinks. Next class, we will look at a couple of problems in heat and mass transfer where there are sources and sinks. After that, we will go into looking at other configurations such as cylindrical coordinates and so on. Okay. So, we will continue unidirectional flows in the next class with other examples of flows with sources and sinks, and then we will proceed later on to looking at cylindrical and spherical coordinate systems. Okay. That completes the separation of variables part of this lecture. You will see it again when we do cylindrical coordinates, but as far as Cartesian coordinates is concerned, this completes the various solution procedures that we have used. Similarity variables, separation of variables, and oscillatory flows. 3 techniques that I have taught you for Cartesian coordinates. We will see them again in other coordinate systems. But before that, we will solve a couple of problems where there are sources and sinks within the flow for heat and mass transfer. So, we will see you in the next lecture, and we will continue unidirectional flows then. Thank you.